This video is brought to you by mywayteaching.com.
Okay, next concept is we have studied about ionization of weak acids. Now ionization of weak bases. Okay, the equilibrium constant for base ionization is called base ionization constant, that is represented by Kb. Okay, that is equilibrium constant for base ionization is called base ionization constant. This is represented by Kb. Then the values of the ionization constant of some weak bases, so that is dimethylamine and okay, ammonia, then pyridine, urea. So like that there are some of the constants, so that is some weak bases, the values of ionization constant of some weak bases at 298 Kelvin. Next one problem, that is the pH of 0.04 mole hydrazine solution is 9.7. Calculate its ionization constant Kb and pKb. Okay, so solution I will write down here: NH2 NH2 plus H2O, NH2 NH3 plus OH minus. From the pH we can calculate the hydrogen ion concentration. Knowing hydrogen ion concentration and the ionic product of water, we can calculate the concentration of hydroxyl ions. Thus we have H plus is equal to anti-log of minus pH is equal to anti-log of minus 9.7 is equal to 1.67 into 10 raised to minus 10. So OH minus is equal to Kw divided by H plus, okay, 1 into 10 raised to minus 14 divided by 1.67 into 10 raised to minus 10, 5.98 into 10 raised to minus 5. The concentration of the corresponding hydrazine ion is also the same as that of hydroxyl ion. The concentration of both these ions is very small, so the concentration of the undissociated base can be taken equal to 0.04 mole. Thus Kb, this is, we know, we represent this base as Kb, that is NH2 NH3 plus into OH minus divided by NH2 NH2. 5.98 into 10 raised to minus 5 whole square, 0.004, 8.96 into 10 raised to minus 7. Okay, then pKb minus log Kb minus log of 8.96 into 10 raised to minus 7 is equal to 6.04. Okay, next problem, calculate the pH of solution formed on mixing 0.2 mole NH4Cl and 0.1 mole NH3. The pOH of ammonia solution is 4.75. okay, solution is NH3 plus H2O, NH4 plus OH minus. The ionizing constant of NH3 Kb is equal to anti-log minus pKb, that is Kb is equal to 10 raised to minus 4.75 is equal to 1.77 into 10 raised to minus 5 mole. Now NH3 plus H2O, NH4 plus OH minus, initial concentration in moles, that is 0.10, 0.20, and this is also 0. Change to reach equilibrium, minus x plus x plus x. At equilibrium 0.10 minus x, 0.20 plus x, this is x, equal to NH4 plus OH minus NH3. So Kb you can write 0.20 plus x into x divided by 0.1 minus x, 1.77 into 10 raised to minus 5. As Kb is small, we can neglect x in comparison to 0.1 mole and 0.2 mole. Thus OH minus is equal to x is equal to 18 into 10 raised to minus 5. Therefore H plus is equal to 1.12 into 10 raised to minus 9. pH is equal to minus log of H plus 8.95. Next, okay, next concept is relationship between what is Ka and Kb. As seen earlier in this chapter, we have studied about Ka and Kb. They represents the strength of an acid and base respectively. You know, right? That is the strength of an acid and at equilibrium constant for a net reaction obtained for after adding two reactions equals the product of the equilibrium constant for individual reaction, that is K net is equal to K1 cross K2. Similarly, in case of conjugate acid base pair, in case of conjugate acid and base pair, Ka into Kb is equal to Kw. Knowing one, the other can be obtained. It should be noted that a strong acid will have a weak conjugate base and vice versa. Okay. Alternatively, the above expression Kw is equal to Ka into Kb can also be obtained by considering the base dissociation equilibrium reaction. Okay. So Kw is equal to Ka into Kb. This is the relationship between acid and base. Next problem, determine the degree of ionization and pH of a 0.0 mole of ammonia solution. The ionization constant of ammonia can be taken from table 7.7. Also calculate the ionic constant of the conjugate acid of ammonia. Okay. solution for this problem. The ionization of NH3 in water is represented by equation NH3 plus water, that is NH4 plus OH minus. Okay, we use hydroxyl ion concentration OH minus is equal to C into alpha is equal to 0.05 alpha. Kb is equal to 0.05 alpha square divided by 1 minus alpha. The value of alpha is small, therefore the quadratic equation can be simplified by neglecting alpha in comparison to 1 in the denominator on right hand side of the equation. Thus, Kb is equal to C into alpha square, or alpha is equal to 0.018. Okay. Next, OH minus C is 0.05. What is putting in equation 1? 0.018. You are getting 9.4 into 10 raised to minus 4 mole. Then H plus is equal to divided by OH minus 10 raised to minus 14 divided by 9.4 into 10 raised to minus 4. What you are obtaining? 1.06 into 10 raised to minus 11. Now pH is equal to minus log of 1.06 into 10 raised to minus 11 is equal to 10.97. Now using the relation for conjugate acid base pair, Ka cross Kb is equal to Kw. We are using the Kb of NH3 from the table. We can determine the concentration of the conjugate acid NH4 plus. So Ka is equal to Kw divided by Kb. Kw is equal to 10 raised to minus 14. This will be 1.77 into 10 raised to minus 5. This is 5.64 into 10 raised to minus 10. Okay. Please note down this problem, and this is the solution what I have solved. Next concept is factors affecting acid strength. Okay, what happens? Factors affecting acid strength means, see, when the size increases, acid strength increases. Okay, acid strength increases. Example, size increases means that is HF, HCl, HBr, HI. This is size increases, acid strength increases. Similarly, electronegativity increases, then acid strength increases. Okay, electronegativity increases, so acid strength increases. So this is factors affecting acid strength. What happens for acid strength? Okay, next concept is common ion effect in the ionization of acids and bases. Common ion effect in the acids and bases. Common ion effect, what do you mean by common ion effect? Consider the example of acetic acid dissociation. Equilibrium represented as CH3, COOH, H plus plus CH3 COO minus, or HA aqueous H plus aqueous plus C minus aqueous. Ka is equal to H plus C minus okay. Addition of acetate ions to an acetic acid solution results in decreasing the concentration of hydrogen H plus ions. Okay. Also, if H plus ions are added from an external source, then the equilibrium moves in the direction of undissociated acetic acid, that is in a direction of reducing the concentration of hydrogen ions H plus. This phenomenon is an example of common ion effect. Common ion effect. This is the example for common ion effect. It is defined as a shift in equilibrium on adding a substance that provides more of an ionic species already present in the dissociation equilibrium. So now, what do you mean by common ion effect? So this is the example for common ion effect, and now I will write down the definition for common ion effect. Okay, I will erase this one. Okay, what is common ion effect? It is defined as shift in equilibrium on adding a substance that provides more of an ionic species, already present in the dissociation equilibrium. Okay, equilibrium. So this is about the common ion effect definition. Okay.